Hi, welcome to another lecture on differential equations. Today we are going to practice systems of 3 by 3 ODEs and see how elimination method can be used in this situation. So 3 by 3 systems are going to give us a little bit of a challenge because they lead to so-called cubic equations. And if you remember from calculus or pre-calculus, you might remember that solving 3 by 3 solving cubic equations a bit more challenging than the quadratics. However, this is going to be a friendly one, and we will be able to manage it without much difficulty. So what were our tools in this case? We said principal traditional way of handling these things is to by simplifying the presentation, and then we are going to use D as a shorthand for the differentiation with respect to t. Okay, so here we have dx dt is equal to 6y, dy dt is equal to x plus z, dz dt is equal to x plus y. So we have three variables, x, y, z. These are dependent variables. We have one independent variable, that's t, typically refers to time. And we want to find x, y, and z as functions of t. So I rewrite this thing as dx. dx is equal to 6y. This is going to help us. It also is going to be more practical than writing prime notation. So this is same as what you would have otherwise used the prime for it. But the algebra that we do is going to work a lot better with this d for differentiation. So the second one is of course going to read dy is equal to x plus z, and the last one is of course dz is equal to x plus y. You already noticed that this became shorter. Doesn't take that much because we are not writing the fractions. Okay, what next? We are going to eliminate one of these variables, either x or y and z. And then after that eliminate the other one until we have one variable left. Now how you choose to proceed in this case is going to affect the look of your answer. However, all those answers are going to be considered correct. So for example, to eliminate y, I might use a substitution, that is find y from here and replace it in the other two equations, and then have something just in terms of x and z. And then and what I obtain, I'll attempt to eliminate either x or z, and then just find the last equation, as the case might be, in terms of z or just in terms of x. So let's go ahead and proceed in that style. So I'll first, so I'm going to substitute for y. So that's how we start. Substituting for y means, well, y is 1/6 of dx. Again, let me remind you, dx means derivative of x with respect to t. I go ahead and replace it here. So here I see dy. Well, that means derivative of 1/6 of dx. Now remember differentiation. You can pull constants out. So that's 1/6. D times d, that would be d squared. D squared then is going to mean second derivative of d with respect to second derivative of your variable with respect to t. So I can write this as 1/6 of d squared x. Now this, what we did here, it looks like what you would have done in Algebra 1, and that's the advantage of the notation of d. It makes this kind of operation looks very natural. Just be aware that we have to have just constants here. We couldn't have any variables. That's a limitation. Next, so I go ahead and replace it here. So I'll have instead of dy, I'll have 1/6 of d squared x is equal to x plus z. and the next equation reads dz is equal to x. Now we said we are going to replace, so instead of y I write 1/6 of dx. Next, I might bring everything to one side so that the equation looks like what we are used to from the prior lecture. So I'll have 1/6 of d squared x minus z is equal to 0. And the second equation, let's write the x first. So it's going to be minus x minus 1/6 of dx, and then plus dz equal to 0. Let's clean this up so that x and z have their proper spots. So I'll have this one as 1/6 of d squared minus 1 times x minus z equal to 0, and the second equation reads minus 1/6 of d minus 1 x plus dz equals to 0. So we wrote this thing in the notation of systems. X and z are variables, and these are known coefficients. What was our plan? Our plan was to eliminate one item at a time. We got rid of y at the beginning. Now here we have to decide if you want to get rid of x or if you want to get rid of z. Well, it looks a lot easier to get rid of z. How would I do that? Multiply the first equation by a d, let the second equation as it is, and then add them up. So I am going to apply d, which means d times the first equation, so it gives me a dz here, and that dz is going to cancel this dz. So let's just write it out. I take this equation, multiply it by d, so it becomes 1/6 of d cubed minus d times x minus dz is equal to 0. So that would be equivalent to differentiating that equation. Okay, when you're looking at the equation, you would have multiplied by number. Now the multiplication by d means differentiating. Second equation, I just leave it alone, minus 1/6 d minus 1 x plus dz equal to 0. We did this just because these two, if you add up the two equations, these two are going to eliminate each other, and that is the reason we call this an elimination method. So I add them, so I'll have 1/6 of d cubed minus d, that is x, and then another one minus 1/6 of d minus 1, that's also times x equal to 0. Well, these are all multiples of x's, so I can add them up. So I'll have minus 1/6 d cubed minus d minus 1/6 of d minus 1. I factored all of that times x is equal to 0. Our life is going to be quite a bit easier if we multiply by 6. Maybe we should have done that from the beginning. When you multiply this thing by 6, I get d cubed minus 6d minus d minus 6 x equal to 0. And we clean up one more round, d cubed minus 7d minus 6 times x is equal to 0. Let me just remind you again, what does this mean? This means the third derivative of x triple prime, minus 7 first derivative of x, minus 6x itself is equal to 0. So we are solving like a third order differential equation in x. How did we do that? You remember we used the method of characteristic equation. We took x to be, for example, exponential of mt, and when you replace it here, you get m cubed minus 7m minus 6 times exponential of mt equal to 0, and that brings you to this equation, which we called it as characteristic or auxiliary equation, characteristic equation. As you notice, this looks identical to that, so with a little bit of abuse of notation, we can just use that itself instead of dealing with this, understanding that now we are looking for a number. Over there, d was derivative with respect to time. So if you accept that little bit of sloppiness in misuse of notation, instead of bringing in a new character here, you can solve that equation itself if you wish. That is perfectly okay in this context. Okay, next challenge we said when we go up to higher order systems is that you are going to have higher order equation to solve. So what is this thing? This is going to be a cubic equation. Cubic equation. We have a little bit of practice with that in college algebra and such, because the full-scale cubic equation is a little bit hard to solve. The formulas are a bit lengthy. So what we do instead is just resort to simple cases where we can actually solve these problems without too much difficulty. Okay, let's just go back to college algebra and refresh our memory on how do we solve this type of equations, assuming that they are friendly equation. Again, if it was full scale with all sorts of random numbers for coefficients and such, that would be taking a couple of lectures all by itself to see what's the equivalent of quadratic formula in that case. But here we resort to something from college algebra referred to as rational root theorem. Rational root theorem, it says if you have an equation and you want to guess your way to the roots, what numbers should you guess? So rational root theorem is looking for cases where the equation is friendly, and then you are trying to find out the roots if they happen to be rational numbers or integers. What do we do? Do we just go randomly try all numbers 1, 2, 3, 5, 5, 6, minus 2, and all sorts of fractions, and just wait for some luck until we get the root? Well, rational root theorem says, well, there is a bit of a smarter way of doing this thing. It says if you have an equation with like a so if you have like equation as in ax cubed plus bx squared plus cx plus d equal to 0. So this is back in college algebra, these are all numbers, a, b, c, d, and x is also a number. We are trying to find out what x happens to be. And we are assuming that a, b, c, d are integers. And of course, a is not 0. What are possible rational roots of this equation? And the theorem says the rational roots are among the rational roots are among by the way, before I proceed, a, b, c, d integers, and they are also reduced to simplify our task, reduced. So if I can simplify by dividing by 2 or 3 or such, you better do that at the beginning. So our roots are factors of d divided by factors of a. So for example, in this case, a is 1 and d is 6 or it's minus 6. Factors of this are 1, 2, 3, 6 in plus or minus. Factors of 1 are just plus or minus 1. The ratio of these two, due to the fact that this is just 1, the ratio of these just turns out to be plus or minus 1 or 2 or 3 or 6. So rational root theorem says if this happens to have a rational root, the only roots that it could have would be one of these. However, if it doesn't have rational roots, or there are some roots that are not rational there, well, that doesn't, we don't have anything to say about that right now. This is just for the simple case that there is a rational root. So for example, we go try. In this case, we have 8 numbers to try: plus 1, plus 2, plus 3, plus 6, minus 1, minus 2, minus 3, minus 6. If there is a rational root, it's going to be one of these. So for example, I try 1. I put 1 here. This is a 1 cubed minus 7 minus 6. Is that 0? Well, obviously not 0. So that is not a root. How about minus 1? So minus 1 cubed minus 7 times minus 1 minus 6. What is that? It's minus 1 plus 7 minus 6. That is 0. So we got lucky that on the second attempt we found something. Now I can go proceed and check these things one by one to see what works and what doesn't work. Option 2 is that as soon as you find a root, factor and simplify your task by looking at a smaller equation. Okay, so 2 ways to proceed. One is check all of these things one by one, see what works and what doesn't work. Remember that you have to find only 3 roots. After you find all 3 of them, assuming you're lucky that all of them are rational, then you're all done. If you don't find 3, then you better go after factorization. How do you factor these things? Well, if d is equal to minus 1 is a root, that means bring this to the other side, d plus 1 is a factor. If d equal to minus 1 is a root, then that means d plus 1 is a factor. So you go ahead and, well, what do? You do a long division or a short division. D cubed minus 7d minus 6, you take it and divide it by d plus 1. This is easy. D cubed divided by d, that gives us d squared. Multiplying back here, I get d cubed plus d squared. Subtract that, or flip the sign of it and add it up. So I get minus d squared, and then bring down the next one, minus 7d. So that is going to give us a minus d here. Minus d times this is going to give us minus d squared minus d. Again, subtract this, so you get minus 6d, and bring down the next one. So I get minus 6, and when you multiply back, if you get 0 remainder, you are vindicated in your assertion that d plus 1 was a factor. This one is checked by the fact that we get a 0 here. What do we get? We get that d cubed minus 7d minus 6. We managed to factor it. One factor, small one, is d plus 1, and the bigger one is d squared minus d minus 6. Now factorization of the second one, or if you have to apply quadratic formula to it, it will be easier because this is quadratic, that was cubic. So, but in this case, we have no problem in factoring the second one as well. So that becomes the factorization of that. Again, remember, it would have been more proper to use the letter m here, but we did a little bit of abuse of notation here to say that our roots are -1, which we already had, d equal to 3, and d equal to -2. Again, let me remind you, these are those characteristic roots that we found in the old notation that we had. Well, what does this say? This says is x. Remember, we were looking for x as exponential of some multiple of t, and the question is, what is that multiple? That multiple is what is the root of this equation. We found the roots, and each of them contributes one function. So some a exponential of this -1t plus b exponential of 3t plus c exponential of -2t. So if you want to compare your answer with your classmates and see how you got it and how they got it, so, we went ahead, eliminated y first, and then z next, and then we ended up with x, and this is how we got the answer for x. Now we can go back and get the other ones again. To compare against your classmates, you have to have the same style of elimination. What is the easiest thing to do? You could, of course, go back and eliminate another variable and redo all of these things from scratch, but that's not advisable. The couple of problems with that, first of all, is just too much work. What's easier than that is go back to your substitutions and just use them. So for example, here you had, here you had y is equal to 1/6 of the x. That tells you that if you differentiate x, you get y. Okay, so that's very easy to carry out instead of redoing all of these things by eliminating x and z and getting an equation for y and solving that, and then try to figure out what's the relationship of the new constants to the previous one. That will be a tall order. This is easy. Y is 1/6 of, so we use the relationship that y is 1/6 of dx. Oh, again, reminding you, that means derivative. So y, I take a derivative of this, I have 1/6. Derivative of this thing gives me a minus 1/6. I have 1/6, and a factor of 3 comes from here, 3/6 of b exponential of 3t, and a factor of 2 comes here, 2/6 of c exponential of -2t. You can simplify these things if you wish, but we can see where they came from, where these numbers come from. These were the exponents that we had at the beginning. How about z? What is the easy substitution for z? Let's go back and see what can we find in our equations. So for example, perhaps the easiest one is to use this, because it's telling you that z is 1/6 of d squared minus 1 times x. Is that right? That is z is equal to that. So let me write that and just carry that out. Z turned out to be 1/6 of second derivative and then minus 1 of x. So I need my x in front of me. What do I need to do? Differentiate this twice. Perhaps I do it step by step. 1/6 of d squared x, then minus x. If you can do it all of it in your head, that would be cleaner. second derivative, that's just going to give you 1. 1/6 of that is going to be, well, 1/6. And then minus 1 becomes minus 5/6. But if you want to write it out, so it's going to be 1/6 of a minus 1 times another minus 1, because you're differentiating twice. Exponential of minus t, and then minus x itself, it will be minus a exponential of minus t. And then we have to do that for b and also for c. Let me clean this up and have it written in a shorter way. Let's see. So let's clean this all up. So that's becoming 1/6. 1/6 minus 1 is going to be minus 5/6 of a exponential of minus t. Then how about the second portion? Second derivative of this is going to become 9. 9 divided by 6 minus 1. So let me write that on what we are going to write. 3 times 3 is 9. Divided by 6, that's this factor, minus 1, then b exponential of 3t. Or just write it step by step. And then finally, we are going to have second derivative of this. That's going to be minus 2 times minus 2, that's a 4. So I was going to have a 4. I have to divide it by 6, then minus 1, then my function, c exponential of minus 2t. So let's clean this up. Minus 5/6 of a exponential of minus t. This is going to be 3/2 minus 1. Exponential of 3t. And this is going to be 2/3 minus 1. So that is my z. If you want to see all of my solutions all at the same time, I had x is equal to, what was it, a exponential of minus t. Is that right? This is my x, b exponential of 3t, and c exponential of minus 2t. Then my y became minus 1/6 of a exponential of minus t, 3/6, maybe we clean that up, b half exponential of 3t, and simplify that one, minus c third exponential of minus 2t, and z became minus 5/6 of a exponential of minus t, b half exponential of 3t, minus c third exponential of minus 2t. Once again, if the order of elimination is different, you could end up with an equation that looks different, because your first equation, if that is x, the coefficients are going to be a, b, c. If you're at the very end, you end up with just y, then equation, and that one is going to have coefficients a, b, c, and the rest are going to be based on that coefficient. So they are all going to be rearrangements of each other in some sense, but if you want to compare, make sure both of you do the elimination the same way. Okay, there are many more examples here, some of them with non-homogeneous equation, meaning we have on the right hand side we have some functions of t as well, typically some polynomial or exponential or trigonometric. but let's leave that for another lecture. Okay, until next time, good luck and God bless.